KAIST and FUDAN University. Thanks for the organizer, Professor King and Professor Wu. The title of my talk is Synchronized Sparse Matrix Computation in Web Information Retrieval. It's a joint work with Professor Golub. I hope you're familiar with this web page of Google. I just this is their technology. It's a homepage for a Google company. I just want to introduce briefly of Google. Google is developed by two PhD students in 1998, Page and Brain. When they were the PhD candidate of Stanford University. After their first year of a PhD candidate, they found that it's very important for the internet of the web ranking. So they told us the heart of their software is PageRank, a system for ranking web pages. From then on, they moved to Stanford and began their company. So this is a story of the knowledge. Now they are millionaire of the Google company. So the key idea is how to rank the page. Since the internet is very popular from the end of 1990s, so this is Google page. The outline of this talk is I want to just introduce some mathematical background of PageRank program and algorithm, power and Arnoldi algorithm for PageRank, and Arnoldi and GMRES method for PageRank problem, and the drawdown condensing field of the Google Matrix, and some application of analysis of micro data mining and the future works. First, we just introduce the mathematical background of PageRank program. We can represent the internet as a graph. It's a graph. I can represent the graph as a static matrix. Static matrix is a negative matrix with column. The sum of column is just 1. And make static matrix more convenient. So that it will be the Google matrix. The PageRank just want to find the dominant eigenvector of the Google matrix. It's called the PageRank. So just this bit. This is a Google matrix. We just want to find the eigenvector of this matrix. And this matrix with the eigenvector 1. The difficulty is that the matrix is very huge. Now maybe 10 billion by 10 billion matrix. So it's a very huge matrix. We will want to find the eigenvector. Google's original idea is a page has high PageRank if many pages with high PageRank to it. So now a lot of companies want to their homepage will be the first. Such as electronic products, sensing, Sony. If you want to search, they want their product will be the first or second, at least in the first page. Nobody wants their products in the last page of the Google of the search engine. So now is a commercial meaning for this PageRank. Of course, for the research, Google also has the Score Google. If you want to search for some citation of your papers, so they can make citation very clearly and quickly. This is Google. Google's original method is called a power method. This is a very classical method for the first year of the undergraduate student. If they were learning numerical linear algebra or numerical analysis. The teacher will always introduce this classical power method for this argument forward. So the idea is very very simple. But fortunately, these two young guys first thought of this idea. Now this idea is a golden idea. They can begin their search engine. Now we call it the world's largest matrix problem. This is called by Moore, the founder of the MATLAB. Once he gave a public talk, he called this world's largest matrix problem, computed Google PageRank. So you can see we can just see this small, tiny internet with 5 pages, 1 to 1 and 1 4, so that you can write this matrix. This column is just the sum of the column is just 1, and this is divided by 3. This is 1 divided by 5. So this is just a matrix. So the Google matrix, you can have some idea. This is the Google matrix. Then we can get to the eigenvector by this method. Power method, you can see just altogether 1, 2, 3, 4, 5 ranks for the code. Just 5 ranks if you want to get the eigenvector. But difficulty is at that time is 5.5 million pages in 2003. Now maybe double the web page, maybe double. So it's very difficult for this huge linear algebra problem. And we want to get very fast solution. The people cannot wait for 1 or 2 days if we want to search something. You just wait several seconds, right? So the Google have the advanced technology for the fast upgrade for this problem. So this is Google's program. Now people have a lot of method on this method. You can see since these two founders leave Stanford, but their company is just close to Stanford University. And we know the father of the numerical mathematics, Jim Golub, is a professor at Stanford University. So he is interested in this topic. So his group designed some algorithms for this PageRank computation. Recently, we saw a paper, Monte Carlo method. So the faster bet for this problem. So our method is the power Arnoldi method. 3 years ago, we gave this our method. The main idea is to construct an orthonormal basis for the current subspace. Then this relationship always holds. The Arnoldi-type method is due to Yimin Wei and Greif in Canada. They give this theoretical result for the eigenvector U, the minimization problem, and can solve it. Now we want to give some comments on Arnoldi method. Arnoldi method converges faster than the power method. Power method is very simple. We just show you it's just 5 lines. Very, very simple. But sometimes it converges very slowly. So we want to speed up this method. So we want to use Arnoldi method. Arnoldi method is faster, but it's complicated. So we want to combine these two methods efficiently through this idea. The basic idea we want to improving the integer vector before restarting. This we can have a theoretical result for this eigenvector. So we can get the estimation of its bound. Our method just already combine the second restart Arnoldi method with the power method. We just want to combine these two well methods together. You can see we just want to make a variance. Power method is cheap, but converges very slowly. The linear convergence. But the second restart Arnoldi method converges very fast, but it serves for computational complexity. And when the matrix is very huge. So our idea just want to keep a balance with these two methods. Now, how to combine the two methods efficiently is a question. We just run this way. First, run the power method. If the convergence is slow, then we move the Arnoldi method, but just only 1 or 2 times. Then move to power method. Power method is cheap, so this is just our idea for our new method. Combine 2 low methods together with the called Arnoldi power method. I just show you the example. This is a classical power method. This is Arnoldi-type method. This is our method. We combine them together. Power Arnoldi. We just show you matrix vector multiplication, since this is the main complexity of this problem. So you can see this is Golub's method. This is the classical power method. And we want to give some theoretic computation to Golub PageRank problem. And the Greif method, subspace method for PageRank can be parallelized, can be computed in parallel and fast convergence. Arnoldi-type algorithm from the eigenvalue probability of point of view, and the GMRES method from the linear algebra point of view.
What is alpha in the previous alpha in the previous graph?
Alpha you mean?
In the graph.
Yeah. Alpha is a parameter they choose by their experience. Now 1.85 seems best. Just the Google told us. We don't know why.
Is it alpha for the rate of combination between power and?
They use a simple combination. They want to if the it's matrix. They choose this one. Of course, you can close to 1 alpha between 1 and 0. So you have a good question. People always will ask which alpha is the best parameter. This is a parameter. So this is choose. So we test the different alpha. This close to 1. You can see this is fastest. But usually people test this one. Well,
the P is the
matrix. Sometimes P have the 0 low or column, so we want to make the matrix irregular. So we put this one. This is vector. This is a rank 1 matrix. So combine them together, rank 1 matrix. So this is. Now people usually use this method. Maybe 3/4 of people working on for the eigenvalue problem for this problem, PageRank. Only 1/4 on this problem as linear equations. Just to solve Gx equals to this. Just solve this problem. You can see this is an eigenvalue problem, right? But if you term 6 is just a linear equation. Three-fourths of people use this method.
Gx equal to x, not lambda x.
No, this is and eigenvalue is 1, very low. Since the matrix is static matrix, we want the largest eigenvalue just 1. So we want the eigenvector. So this will be x. And then if you move x, this is a linear equation. From mathematical point of view, they are equivalent. But for the algorithm point of view, this for the eigenvalue is much better than the linear equation. So this is very interesting. If you solve this linear equation, usually not so good as this one. This for the eigenvalue. So, now we want to GMRES method now is very popular for the linear equations. Generalized minimal residual method. This for the linear equation is very popular now. But if you want to use for this PageRank problem, of course you can solve it use this method. Now we want to compare this classical with Arnoldi-type with GMRES. We want to ask what's the relationship between these two methods. Are the technicals from such space the same? Is there computable formula between these two approaches? Which method is better? We just want to answer these 4 questions. People usually think of these questions for these 2 methods. First one, what's the relationship between the search subspace of the 2 approaches? We prove that with the appropriate entity back, 2 approaches indeed share the same search space. You can, this is for the cross subspace. They are the same. So theoretically they are equivalent. And the second question, the 2 approaches are different. Since the GMRES method is optical projection method, and Arnoldi can be understood as orthogonal projection method, when the optical and when it's also orthogonal. And the second is whether they are mathematically equivalent. We can tell you this is for the GMRES method, and this is for the Arnoldi method. And we can give you a formula between the difference of these 2 approaches. This is for the Arnoldi, this is for GMRES method. The angle of these 2 vectors by cosine. We can show you the formula. And then which method is better? This is dependent. This is a problem dependent. Sometimes Arnoldi is better, sometimes the GMRES is better. And Arnoldi for PageRank, we can give this theoretical result for this approximation for the argument and this sign. And the GMRES, we also can give this theoretical result. And Jordan Canonical film, we want to give some comments. And we find a paper in Sun Matrix. They have made a mistake. We corrected them. So Professor King just asked the question for the after this one. This is the original matrix. If we want them irregular matrix, so you have a linear combination. This is the rank 1 matrix. So this is Jordan Canonical field. We want to give some theoretical result of the Google matrix.
Yes, the matrix P is simply positive definite.
P just not significant. P just a low statistic matrix. Statistic matrix. No negative matrix. No negative. Its column, the sum of the column is just 1. So usually it's not positive definite. No, not having these properties. And this matrix E just rank 1 matrix. Rank 1 matrix. Also low static matrix. Now we want to, this is Jordan Canonical field. We want to give some theoretical analysis of this Google matrix. We want to do condition number. Condition number is smaller the better. This one, of course, this one the smaller the better. So we want to analyze this diagonal matrix. Diagonal matrix. And we discussed several special cases. First, the diagonal matrix. So we can get this result. The condition number with the infinite norm. This is one case. The difficult problem is how to choose the optimal match D. Even D is a diagonal and no singular. We consider Jordan-Knapp field. Then we consider three cases. This is a simple case, diagonal matrix. This is Jordan block. And this one. This is the area here. The three cases. Now we can solve it by the minimum condition number. Just this one. If we choose the diagonal matrix D in such case, and the minimum condition number is this one. And case 2, the similar we can analyze. This is another case 3. We can choose the suitable diagonal matrix such that condition number is minimum. Now we want to give the process with a GMRES for the micro data mining. So the idea is the same. The PageRank is now very popular. We just mathematician. We just want to test the problem, and we never get the real data. We just get some data from the web. Is open data, is free for us, but it's very small compared with the real data. Just a toy problem. But now people want also interested in the GMRES. So they use the same idea with this problem. If the G, we'll see which gene is close to the alias and which one is better. So we want to just, this is a high differential expression, this no differential equation, this error in the network.
Given your web matrix,
yeah.
How can you evaluate that your P is good?
You mean how evaluate P is good?
Yeah.
Or not?
How can you tell that P is good?
Oh, now we just use the sample from the web, so we just take it. We just test it with our method compared with the classical method. Compared to which one is fast or accurate. The main advantage of our method, we want it fast. It seems not important, it's very accurate for the solution. Just have 2 or 3 digits, so okay. If you can distinguish from the A vector, so it's okay. Just the fast important is more important than accuracy. So this is just. So the other question, the convergence depends on this parameter. Different parameter with the different convergence rate. So you give a question how to choose this one. But Google only tells us this one. They never tell the reason. They never claim they are their algorithm. Just Moore told us they use the power method. He gave a public lecture. Just the access and the linear algebra very important. He gave the example of the Google. He said they use the power method, but in the real computation, we don't know. We don't know. This is a secret. This is a secret. Now, a lot of computer science or mathematics, people just doing research, just for the mathematical point of view, want to solve this problem. But we never give their real data. Their language is very huge. Now we just 100 of their data, so we just test. So this for the GMRES, for the PageRank problem, now just maybe just a training for the student, and we never get better than the Google. They never get better. So we will try the GMRES. So GMRES, now the data we have the sample data is not large, so it can use. So we want to.
So the age in your networks are directional or indirectional?
You mean?
I mean the age. Those links in your networks are directional or indirectional?
Rational. Now, if we see the mathematical problem, it's almost the same as the PageRank problem. They're almost the same. Now we just solve this problem. as we just use the data. So this is the Arnoldi method for the GMRES problem. Just want to solve this vector U minimization. Our modified Arnoldi method put this vector here. Put this vector here. So we want to solve them quickly. Solve this the same problem. Now we just choose the V n plus 1. We choose the suitable vector such that more quickly solve this problem. Now we get this theoretical result for the problem. Now we just show you this is our the node method. We'll compare with others. This is Arnoldi method. This is with our modified Arnoldi method. You can see our CPU time is much fast. This is CPU time in seconds. So if we modify the Arnoldi method for this problem, we can get the fast. But the matrix is just small. This small data. We want to find the larger data. This is just a test problem. Use this our numerical method. Now the future work is the structured algorithm for PageRank. Now people are more interested in the graph theory. And PageRank, people think this is graph theory. This is a matrix close with the graph, and the matrix is very sparse. Very sparse. So people use the theory of graph theory, want to solve this problem quickly. So, and the tensor model for PageRank and GMRES. And there's new models for solve this problem much quickly. This is the end of my talk. Thank you for the attention.
Any questions, any comments?